Okay, so let's start. So hello everyone, and welcome to the fifth session of Fmics. In this session, 3 tool papers will be presented, and we had asked the tool paper presenters to make 15-minute presentations instead of 20-minute presentations. So we estimate that this session will end a little bit sooner, around 6 p.m. probably. So as usual, please use the Zoom chat or the Q&A feature of Zoom to write your questions that will be answered after each presentation. And let's start now with the first paper presentation. Next, David Gelesus is going to present the paper titled PROB B2 UI, a Java-based user interface for PROB B.
Hello, I'll be presenting PROB 2 UI, which is the new Java-based user interface for the PROB animator and model checker. Now, I'll start out with a short bit of history because this is not the first user interface that we have developed for PROB. Shortly after PROB development started, around the year 2000, we also started developing the first user interface for PROB, which is based on the TickleTK toolkit. We chose TickleTK mostly because of its good integration with Six's Prolog, which is the language runtime that PROB is implemented in. This TickleTK-based user interface is still in use today. In 2005, we also started developing a plugin for Rodin in order to use PROB with event B models. This required developing a new separate user interface based on Java and Eclipse in order to integrate PROB natively into Rodin. Now, since we already have two user interfaces for PROB, why are we working on another one? Well, there are multiple reasons. First of all, the TickleTK user interface sometimes simply isn't very intuitive to use, in part because of its long development history. And we also encountered some technical problems with TickleTK, such as long-running operations completely blocking the UI and difficulties to install TickleTK as a dependency for end users. The Rodin plugin doesn't suffer from any of these problems. It can simply be installed into any Rodin installation, but its main disadvantage is that it is tightly coupled to Rodin. It can only be used with event B models, and it is missing many features that PROB otherwise supports. So in 2016, we started work on PROB 2 UI, the new user interface for PROB. This user interface is based on JavaFX and can be easily installed on all major operating systems without having to worry about dependencies. PROB 2 UI reuses the same architecture that was developed for the Rodin plugin, where the user interface is kept separate from the core of PROB. This improves responsiveness because the core cannot block the UI and also makes it more robust because errors in the core don't automatically also crash the UI. PROB 2 UI also has some other new and improved features, which I'll get into later. Now I'll be demonstrating some of the main features of PROB 2 UI. I already have it open here, and I've loaded a simple classical B lift example machine. One of PROB's main features is the animator. Now you can see if I set up and initialize the machine here, you can see PROB has generated a list of operations that I can execute in the current state in their parameter values. So I can, for example, go and move the lift up and then move it back down again. Now, if we want to see what these operations do, we can switch over to the state view here, and here we can see the current state of the invariant and constants and variables, and here we can see the current floor variable. If I move the lift up again, you can see the current floor go up. Now all the operations that I execute here in the operations view are recorded in the history here. I can view the history, and I can go back to previous states here, go here and then execute a different operation. And it's also possible to take this history and save it as a trace file, which can then be replayed later using the trace replay feature. Here I already have some trace files saved. I can replay them, and this will execute the same sequence of operations that has been saved in the trace file automatically, and will return to the saved state here. Now you've already seen how you can inspect the state of the model using the state view here, but this just shows you the raw values of the variables, which is sometimes not very understandable or intuitive, especially with larger and more complex models. For this purpose, PROB2UI includes a visualization tool called VisB, which you can see here, for example. VisB allows you to create custom interactive visualization based on SVG graphics. For example, here's a visualization for this lift. You can see the current position of the lift here. It's in floor 0, and if we move and we can move the lift up here using the visualization. And now that it's arrived here, we can open the door and close it again. This visualization can also be saved as standalone HTML file, either just the state, or you can also export the entire transition history as an HTML file, which can then be viewed in the browser. PROB2UI also supports some other visualization features, such as the graph visualization here, which can be used to display various aspects of the machine as a graph. For example, here I am using the state space expression projection feature, which lets me enter a B expression and see how its value changes across states and how these states relate to each other. For example, here I am looking at the current floor variable, and I can see that, for example, if the current floor is 0, that can only go exactly one floor down or exactly one floor up. There's no way for it to change from 0 directly to 2 or the other way around. There are also some other graph visualization modes that can be used here. For example, the formula tree modes, which you can use to here PROB will take, for example, the invariant and will decompose it into individual sub-predicates, and these predicates into the expressions that make them up, and so on, and will show each sub-predicate and sub-expression's value here. This can be useful for debugging if part of your invariant is false and you want to see exactly which part that is. If the built-in visualization features of PROB2UI are not sufficient, there's also a plugin mechanism which can be used to implement complex custom visualizations. These visualizations can use any JavaFX components that are available, and can also use arbitrary Java code to, for example, use external data sources together with the model. This has already been successfully used in a demonstration of the ETCS European Train Control System hybrid level 3 concept. Here you can see a short excerpt of this demonstration. The visualization at the bottom is generated by a PROB2UI plugin. This plugin is receiving data about the positions of these trains on the tracks and is transmitting that data into the B model, and then uses that to generate and update the visualization here. Hello, I'll be presenting PROB2UI, which is the new Java-based user. In PROB2UI, you can also use PROB's verification features. If I open the verification section here, for example, we can use PROB's model checker. PROB supports both explicit state and symbolic model checking. Now, if I open the model checking window here, we can, for example, use the model checker to search for invariant violations or B assertion violations or deadlocks or some other errors such as well-definedness errors. You can search for goals, search for state that where a specific predicate is true. You can also use say if it should use breadth first or depth first search. Now, if I run the model checker here, now for this example model, I know that the model checker won't find any counterexample. Here it will say that everything is okay. PROB can also check LTL formulas. Now here I have some example formulas already configured. PROB supports the usual LTL operators, globally, finally, and next, but it also supports some advanced operators. For example, it supports past LTL, and it also supports some B-specific operators. For example, this operator here, this operator is true if in the current state this operation was executed. There are also some other B operators, for example, to check if an operation is enabled or if the current state is a deadlock state. Now, if we check this LTL formula, here PROB will find a counterexample, and here PROB2 UI will automatically go to this counterexample in the animator. So if we look in the history view, we can see which sequence of operations had to be executed to violate this LTL formula here. And we can also we can just view the trace. We can also go back and forth in the states and inspect the variables, for example. One feature recently added to PROB2 UI is a simulator, which is called SimB. Now, I won't be explaining all features of SimB in detail here, but the basic concept is that you can configure operations to be executed automatically based on certain conditions. This can be done either deterministically or probabilistically. For example, that one operation is more likely to execute than another one. It's also possible to configure delays between operations to get a kind of real-time simulation or just execute without delays in accelerated time. Together with the simulation, you can also use certain statistical techniques like hypothesis tests to check that a certain operation is being executed an expected amount of time in the simulation. After the simulation is run, you can also save a simulation run as a time trace, which is like a normal trace that saves the sequence of operations, but also includes timing information. And you can replay this time trace later, including the timing. Here I have a time trace loaded. Now, if I execute this, we can see the time is passing here, and at certain points in time, operations are being executed. Now, if I open VisB, we can see better what exactly is going on here, how the lift is opening and closing and moving up and down in the simulation here. Finally, one feature that PROB2 UI adds compared to the old TickleTK UI is project management. Now, a project in PROB2 UI behaves more or less like a project in an editor or an IDE. It's basically a collection of related files stored together. But in addition to just listing files, you can also save specific preferences for each model. For example, if a certain model needs PROB configured differently to make the animator work, you can save that in the project. Also, if you create any trace files or perform any verification tasks using PROB2 UI, that will also be saved in the project file. So for example, this list of trace files is saved in the project, and I can replay these traces directly here without having to pick them from the hard drive first. And similarly, this list of LTL formulas that I showed before, this is also stored in the project and can be checked quickly. Under the project view, there's also this overview view here, which can be used to see the checking status of all machines in the project. For example, here we can see the lift machine that we have here. Everything is green except for LTL formulas where we know that they are red, and we have this other machine here which has traces that haven't been replayed yet, and an LTL formula that has already been checked. In conclusion, PROB2 UI improves over the TickleTK user interface in a number of ways, although we have not achieved feature parity yet. There are still some features that are only available in the first TickleTK user interface, and sometimes the performance and resource usage of PROB2 UI is not as good as the TickleTK version yet. So we can repeat the advice that you should never underestimate the effort needed to completely rewrite an application, even if, like in this case, you're only rewriting the user interface. But even with the current feature set, we have been able to use PROB2 UI successfully in practice. Below you can find the homepage for PROB2 UI, and thank you for listening.
Okay, thank you very much for the interesting presentation. The presented evolution of the graphical user interface of the PROB tool is a very nice addition to the tool. And I see a question in the Q&A feature. So maybe let's start with that. So
do we have to read it, or?
I can read it or you can read it. Okay,
So, I mean, one question that this, maybe I'll answer the second one first. Which UI solution is new and you would recommend other formal methods UIs to have? And what I would always recommend is things like animation and visualization in particular. So that we found to be very useful. Also myself, when I write models or try to understand other people's models, quite often I do a visualization that helps me to understand the model. I mean, which UI solution is new here? I mean, David just explained it. I mean, the project management can be very useful, but in that some other tools have that already, like Atelier B or Rodan as well.
Well, I think referring to the first question, I think the one inspiration is the predecessor, the PROB-TK.
Yeah.
But most of the UI features we discussed together what might be useful, and then we just implement it, and then we see how it works in practice. So I think one of the UI feature that is really useful is the, as you said, the project management, because there you can persist different configurations and also persist the project together with the machines just to recheck the LTL formulas and so on afterwards.
Yeah, and I guess the trace replay, storing the traces and being able to replay them, that is something, a new feature that the other versions of PROB don't have, and which is very useful. Yeah. In the original inspiration of the UI with the animation view, history view, state view, actually, I mean, that dates back from the TK version, and which also was inspired from another tool then at Southampton called ARC by Peter Henderson. So it had this 3 panes to, and which I think that's something that has also been useful, coming back to the look. Yeah.
Okay, thank you. That was a question posed by Bernd Westphal, and actually also related to that. So such user interfaces are often very welcomed by the community and increase usability. So do you think, also to relate with Joe's keynote, do you think that this is a way to go for increasing the adoption of formal methods in industry, or a way to go?
Yes, I think it is definitely a way to go. Yeah, so I know that we have used it, for instance, at Thales to show the formal models to domain experts who were not able to read B, and they have been able to play with the model this way and actually find errors in the specification. So it has been very useful. And at ABZ, there was a talk by Jonathan Hammond from Capgemini, formerly Altran Praxis. They're conducting various case studies also in EventB, and they say that it's very useful to them, and to communicate with industrial people.
All right, thank you very much. So there are a couple more questions, actually a lot more questions.
Yeah.
So what technologies have been used? Which platforms are supported? This is asked by David DeHarb.
So platforms, currently we provide binaries for Linux, Mac OS, and Windows. Right?
Yeah, all 3. We support all 3 operating systems. What technologies have been used? As mentioned in the presentation, we use JavaFX. And I guess it's already Java 14 or 15 or something like that. But it also supports Java 8. Yeah. But it's together it's built together with PROB2 UI.
Yeah, so, and now we provide it as a standalone binary, so you don't even have to install yourself Java or anything.
Oh, that's really cool. Okay, so another question from, sorry?
Yeah, okay.
From Robert Rubens, how is the VSB UI scripted? Is it a DSL or some declarative SVG configuration generation?
So it is a SVG graphics, and for the configuration we have a separate JSON file to interact with the B model.
Yeah, in the JSON file you specify, for instance, in the SVG graphics file, you have to give identifiers to the individual objects you want to modify, and then in the script file you say based on give a formula, how to change a given attribute of an object identifier. So you can say set the color to red if the value is greater of X in the model is greater than 100. But this is a B expression, the condition and the value, and then you need to refer to IDs in the SVG file. So the idea was to make it lightweight, right? So you don't have to learn any programming language. I mean, you have to know the identifiers of in the SVG file, and you have to know the variables of your model.
Right, very nice. Okay, so also by Robert Rubens, are counterexamples of certain formulas visualized, or are they just a list of events plus a description of the current state?
Yeah, so I mean, for safety model checking, yes. When you have the trace then in the animator and you can do what you want. I mean, if you have a visualization, then you can obviously also visualize the counterexample in VisB, for instance. And as David mentioned in the presentation, export it as an HTML file, which you can send via email to somebody else, and then that person can play and inspect all the values and all the steps of the counterexample. I mean, for LTL formulas, actually, the counterexample is a lasso. And I mean, that in the video, you could see it that actually the lasso, I think, was shown, the last step of the trace was the lasso. Yeah. I mean, that is something we still want to do to present a bit nicer, to show that it's actually a loop you have to execute to violate the LTL formula.
So you can also combine many validation techniques. For example, you could apply multi-checking, and then you get a counterexample, which is viewed in the history view. If you want, you can save the trace, but you can also use the visualization tool, for example, to decompose the invariant to see which part of the formula is actually violated.
Oh, wow, that's very interesting. And by the visualization, you mean the simulator that you showed in the video?
Excuse me?
So so in order to see the counterexamples, to visualize the counterexamples, do you use the simulator of the tool?
You could detect a counterexample by simulating, but you could also apply multi-checking. This also provides.
But here, I think you meant probably VisB in the visualization, and you know, when you can inspect
Yes.
the values of the variables, and you can actually type your own formulas and look at that, the values of that formula, of that expression of interest. Yeah.
So there are many ways to inspect counterexamples.
Okay, and you also mentioned exporting counterexamples and traces, also formulas. So what are the export functionalities of the tool?
Yeah, I mean, traces can be persisted as a JSON file. I mean, you can export it as an HTML file. And that's for the traces. I mean, currently the Java FX UI uses mostly JSON for many of the exports. Right? And also the time traces is also JSON, right, Fabian?
Yes, it's also JSON. It's in the SymB format.
Yeah.
And yeah, it's.
I mean, the PROB, the prolog part has a few other export options, but I don't think we have put them in the. You can also export them as a textual B file in B notation, for instance, the traces. And this is maybe better for humans, but less useful for other tools or for replaying.
Very nice. So, and the last question in the Q&A. So David Basil is asking about the new features added to the UI project, for example, project administration. How were these new features chosen? Were these required by users?
Yeah, good question. I mean, some of them, yes, come from other users, some from ourselves, from the usage. I mean, like with the project management, quite often you work on a subset of various models in your project and various refinement levels. And so you want to group them together. And it evolved. I mean, we knew we wanted to associate maybe various preferences, have various configurations for the same model. And yeah, I mean, we didn't do a systematic study, I have to admit, right? So we didn't do an evaluation or a questionnaire, or maybe we should have done that.
So sometimes it's something like we would like to have a feature, then we implement it, and afterwards we see that it is not as user-friendly as we hoped. And then we think about what we could improve so that it gets more user-friendly. And then it's how the tool evolves.
Okay, thank you very much for the detailed explanations. I see a last question actually in the chat. What is the cost to overlay SVG-based images over a model?
Yeah, I mean, that depends. I mean, quite often that is not a bottleneck. I mean, I know that some people have created large SVG files with maybe hundreds of observers, and then it can get maybe a bit slower, but quite often it's still very fast. So we haven't had any real performance issue. Right? Quite often, the more the performance issues are in model checking or in the solving complex constraints. Visualization actually works pretty fast, and especially the HTML export can replay the trace very quickly. And I mean, yeah, so the browsers can adapt the SVG files quite quickly.
I also think that the HTML export also encode the visualization for each state. So there is no replay, it's just the state visualization.
No, it is a replay, but yeah,
it's not a technical replay, so it doesn't work on the model directly. So
no, it doesn't work on the model. It has hard-coded all the trace, all the values. Yeah. But the cost.
Thank you very much. Yeah, sorry.
Thank you very much for the feedback. Thank you.
Yeah, thank you very much.
Please go ahead. Okay. Thank you so much. So these were really detailed explanations, and the presentation was very interesting. So thank you again. And I think we can move to the second presentation of the session. So Roberto Brutomesso is going to present Intrepid, a scriptable and cloud-ready SMT-based model checker.
Hi everyone, my name is Roberto Brutomesso, and in this talk I will present the tool Intrepid, which is a scriptable SMT-based model checker. Intrepid is a circuit-based symbolic model checker. It means that the model and the property to be verified are both represented as a circuit. Then the circuit is taken and translated, together with its evolution over time, as a set of formulas. And the formulas are passed to a solver to check for satisfiability. The potential solvers that one could use for symbolic model checkers are, for instance, BDDs, SAT solvers, or SMT solvers. And this latter is the choice for Intrepid. And in particular, we rely on the efficient Z3 solver from Microsoft. The encoding into an SMT solver allows you to go beyond Boolean types. And this also helps into a better preservation of the structure of the model compared to, for instance, an encoding into BDD or SAT, where you will have to bit blast all the formula into individual bits. So what is the motivation behind the building of a new model checker? Well, I'll take inspiration from a quote that you see on the screen from the Fmics website. It basically says that the use of formal methods is still quite limited because it's sometimes very difficult from an engineer to pick up with the notation and the difficulties that are intrinsic in taking an off-the-shelf tool and start to use it. And this is something that I have encountered also in my experience in industry. Basically, most of the times you have language issues. It is difficult to understand the input syntax of the tool you are going to use, or into translating your problem into this syntax. Then there is lack of libraries. Sometimes the language of the tool does not support the use of libraries, so you have to take many different files, combine them together with an external tool, and do any sort of parsing and writing and stuff like that. Also, one thing that I think many model checker are missing is the lack of interactivity and scriptability. The input languages are static. They are not, so to speak, scripts that you can use, modify, and program in the way a modern programming language works. And another missing feature is sometimes the lack of solving multiple targets together. Some model checkers just target solving one target per time, one property at a time. So what you are seeing on the screen right now is a first example of an Intrepid script. As I said before, with Intrepid you can basically write circuits, for which I gave a representation on the left, whereas on the right you have the actual Python script that you can write by importing the Intrepid library. So for instance, with the highlighted instruction, you can create a constant, in this case a constant true. Then you can create inputs, or you can create latches. And by means of using these basic blocks, you can create all kind of models and properties that you would like to express. And if you use an advanced IDE such as Visual Studio Code, you will be provided with a set of suggestions once you create the context object, so that it will be easier for you to find what are the available APIs for the tool. And because Intrepid models are essentially Python programs, Python scripts, it is very easy to create libraries. Essentially, you can put the definition of your circuit inside a function and then call it later on. So in this case, let me blur out the definition of the clock, which I wrote in the previous slide as well. And let's focus on the yellow box at the bottom. So in this case, we just create a context, and then we can, with two instructions, allocate two different clocks using the very same context object. In this case, we can reuse the design that we have written before twice in a very simple manner. So once you have written your model, you would like to have the confidence that you have written the right thing. So one way of doing that is with the simulator. Intrepid provides you with a simulator that can be used to simulate your design. So back to the example here, we create again a clock from the previous slide, and then we use the context to allocate a simulator. With these instructions, we can tell the simulator which values are important to be watched during the simulation. Then we create a trace. A trace is essentially the set of input values that are evaluated at each timestamp. So in this case, we set the very first value for the input, we set it to 0. And then we let the simulator simulate the trace for 10 timestamps. And here on the right, you see what is the output of the instruction on the left. So basically, we can take the trace now that has been augmented with the values from the simulation and print it out as a pandas data frame, pandas being a very popular library for data science in Python. The same thing you can do with the plotting. So you can use the available infrastructure for plotting a data frame and have your graphs displayed on the screen if you use some framework like UPython, for instance. So once you are confident with your design, you would like to write and check properties. Properties in Intrepid are called targets. A target is essentially a Boolean signal in the constructed circuit. And with the engines, you can check for a target reachability. So you can check whether a target ever gets value 1. The engines that Intrepid provides are multi-target. It means that you can feed the engine with n targets at a time. And then you can start the search for reachability. When a target is found reachable, the search is paused. The counterexample for the target that has been found reachable can be retrieved, and then the search can be resumed without the target that has been just found reachable, which is eliminated from the set of targets to be searched for. The engines that are available in Intrepid are essentially three. There's a classical bounded model checker, which is incomplete, meaning that you can reach a target, but you cannot prove that the target is unreachable. But it can be augmented with temporal induction, which makes the approach complete. Then there is an optimizing bounded model checker. The goal for this engine is to find traces, so counterexamples, that satisfies the most targets at once. I will show after this slide an application that makes use of this particular engine. And essentially, the implementation relies on the optimization algorithms that are implemented in Z3. And finally, there is another complete engine, which is called inside Intrepid backward reachability. It's our own algorithm based on pre-image computation and quantifier elimination. In a couple of words, essentially, you take the property, the bad state that you want to reach, and you apply the pre-image operator backwards over and over until when you have found all the reachable states backwards, or you have encountered that there is an intersection with the initial property, with the initial state, sorry. In this slide, I'm showing an application for the optimizing bounded model checker. And it's basically automated test generation in MCDC. This is an application that is very relevant in avionics. Essentially, what you see on the left is a requirement composed by Boolean conditions on several inputs. And the goal for the test generation is to find some tests that will satisfy the MCDC criterion. Without going into the details, essentially you have to find pairs of tests for which the output is different and just one input is different as well. So in this case, the input 1 evaluates to false and true, and all the other inputs have the same value, and the result is again false and true, which means that input 1 is relevant in this circuit. If you do the same for all the other inputs, if you find a pair of tests for each inputs like this, then you have proven that your circuit satisfies the MCDC criterion. And the optimizing model checker comes into the picture here because you don't want to find all the possible tests that are respecting this condition, but you always want to find a minimal one. So you optimize, in this case, for finding the minimum amount of tests that will satisfy the condition. One last word is about the REST API. So far, I have shown you Intrepid in terms of Python scripts, and that's the main application of the library. But you can also run Intrepid as a standalone container using the famous Docker program. So if you run the line that is now on the screen, you will be able to run locally a server, and this server exposes a REST API. So essentially, you can, by means of the classical post, get, put, and other commands, use the API of Intrepid as if it was the Python API. You can create a context, you can create inputs, and so on. Essentially, all the APIs for creation, running engines, simulating, they are all implemented into specific APIs which are documented. So as you can imagine, this is particularly useful if you want to place the model checker on a remote server, for instance on AWS or another cloud provider. So you can create as many instances as you would like, and you don't have to rely on the local hardware to do your computations. So in conclusion, I have shown you Intrepid, a model checker that features a rich Python and REST API. There is a lot of related work on the topic and other tools, and I suggest you to check the paper for the complete and exhaustive list. And moreover, there's another video which I have placed on YouTube where you can see more examples, more interactions with the terminal. I show you how to run the tool, install it, and so on. So you can just click the link and check it out. Thank you everyone for your attention, and if there is any question, I'm here for you. Thank you.
Thank you very much, Roberto, for the nice presentation. There is one question in the chat from Fabian. Fabian asks, the circuits examples you have shown strongly reminds me of some looser examples. Did you apply Intrepid on looser programs? If yes, how does it compare to Kind 2 regarding the performance?
Okay, so I indeed have used the Lustre programs, but mostly to because they were one good set of benchmarks available. So I used them mostly to build the tool and to make sure that it was running the way it should. As far as the comparison to Kind 2, so there is a bit of a difference between the interpretation that Intrepid and Kind 2 uses for the integers. So the Kind 2 interprets the integers as infinite precision, as you know, integers that can go from 0 to infinite, so to speak, whereas my tool is bit precise. So there is a difference in the semantic. That's why I could do a comparison, but it would probably not be correct because the semantic of the interpretation of the model is different.
Okay, this question also relates to the next presentation, which will be on Kind 2 actually. Daniel says, now Kind 2 also supports machine integers.
I will then try to run the comparison. I know that now Kind supports the machine integers, but for the scope of this paper, there was not enough time for me to create an exhaustive comparison. I would also like to compare to other tools as well, not just Kind 2. And so it's another, you know, a lot of work to do, and but I will do it eventually. Okay,
thank you very much. So there are other questions also now in the Q&A feature. So the first is, nice tool and nice talk. Could Intrepid eventually replace or compete some tools of CAD software suites from, for example, Cadence or Synopsys?
So at the moment, Intrepid is just the backend. So I know that Cadence and Synopsys, they use their own backends as well. So for instance, they use the ABC model checker, which is a bit precise, and it's not SMT based, so to speak. So replace, it's a big word. I think that the better word is to complement, perhaps. So maybe if you have a different way to represent and you know, put the problem of your circuit in a different way, you can put it either bit blasted, or you can put it in a more SMT style. And in that case, you can have several technologies, several backends to use, and Intrepid could be one of them.
Okay, great. Zen is asking, he's saying also very interesting talk. does Intrepid convert a fully verified model to an HDL model, such as VHDL, System Verilog, etc.?
So I don't understand if you mean if we have a front end from VHDL or something like that into Intrepid, or if there is a way to convert an Intrepid model to those kind of representation. And but no, in both cases the answer is no. You can just create the model as it is. As I said before, this is just the backend, so it has its own language, its own environment, which is the Python word. And you know, the only front end that I support right now, it's the Lustre programs, and a little bit of a language from the PLC world, which is the structured text. So these two are the main front ends that are currently supported, but VHDL could be in principle translated as well into the language of Intrepid. So there are a number of tools out there. One of them is the IOSys, for instance, which is developed, I don't remember exactly where, perhaps in Austria, at Linz. And yeah, it's something that it could be done.
By structured text in PLC, you mean ladder logic?
No, the ladder logic is another language as well. So in the PLC, you have 5 languages. You have the structured text, you have the ladder logic, you have the functional block diagrams, and other 2. And they are semantically all equivalent, but they are written differently. Structured text is more like C or Pascal kind of language. It's not a graphical one.
Okay, sounds good. And there is also another question from Zen. Does Intrepid apply to only synchronous design, or can also work with asynchronous circuit design and verification tasks?
So the models of Intrepid are just, you know, synchronous things. So if you have a way to translate the asynchronicity into a synchronous model, then of course it would apply, but it's just like synchronous models as SMD, or you know, those that are supported by the Lustre language. But no, asynchronicity is native of this language.
Okay. Zen, are you covered with these answers? Yeah, he says thank you. Okay, perfect. I have just one last question. So since it's available through a Python API. So can I use Jupyter to program and run?
Yes, exactly. One of those pictures that I was showing in the slides is taken from Jupyter, exactly. So you can just install Intrepid as a package and then start using Intrepid in Jupyter.
That's amazing. That makes it very easy to use also.
I hope it helps.
Okay. Yeah. Thank you very much. Very nice work, very nice presentation. Yeah, thank you.
Thank you.
Okay, if not, I think we can conclude the session here. So thank you very much for the presentation. Thank you very much for answering the questions. Thank you to all the presenters. I think it was a very interesting session. And we're going to take a break now and see you back at 6:30 for the last session of Fmics. So see you soon. Thank you very much.
Thank you.
Thank you.
Thank you. Bye.
Bye.